Dearly Father, we thank you for this morning. I thank you for these students and their hard work on the homework. I just pray that that would pay off in their learning. I just pray that you be with us today. Help us to glorify you, Lord, in what we do this morning, Lord. In your name I pray. Amen. So turn in your homework. Just pass that away. So go ahead and let's see, while you guys are doing that, I'm going to attempt a harder integral. Now, I think it's been a few years since I've done this. So there is a certainly a non-trivial chance that I'm going to get stuck on this one. So I'm going to try to integrate secant cubed theta d theta. I have a vague recollection of how I did it before. See how it goes. Yeah, secant squared, that one's easy, right? For shame if we can't do integral of secant squared, okay? And basically, even powers of, like secant to the fourth is way easier. Before I attempt to take on that boss, let me take on this one. Like secant to the fourth theta, that's not too bad, because what that is the integral of secant squared theta d theta, right? And so I can convert secant squared to tangent squared, right? Because I've got this formula. I've got tangent squared theta plus 1 is equal to secant squared theta, right? So this becomes the integral of tangent squared theta plus 1 times the derivative of tangent theta. So you can see that I just get 1/3 tangent cubed theta plus tangent theta plus a constant. So you see, even powers of secant, they're not so bad. Odd powers, though, we already dealt with. Remember last time I showed you the integral of secant theta was what? We worked it out. It was the natural log of the absolute value of secant theta plus tangent theta plus a constant. I advocate the view that this is something you should memorize because it's kind of a pain to derive. And memorizing that formula would take up just as much mental capacity as memorizing how you derive the formula. So, yeah. We do need that integral from time to time. Comes up in certain examples. I got everybody's homework? Excellent. Thank you. Oh. Now put the grader to work. All right. We'll try to get these back to you before too long. We won't always be able to get them back before the test, but we'll try. But especially the homework right before the test, if you need to compare it against the solution, make yourself a copy. But I should hopefully have the solution to that posted a little bit later today, okay? All right, so how should we try to do this? I guess what I might do is try something like, this is the integral of what? Secant squared theta times secant theta d theta, which is what? Let's see, we just said what? Tangent squared theta plus 1. All right. So what does that give me? That gives me the integral of secant theta d theta plus the integral of tangent squared theta times secant theta d theta. Now this we got that piece, right? That's good. Let's see here. So we can try some kind of like integration by parts on this other piece. Let's see here. If I rewrite this as the integral of tangent theta times secant theta tangent theta d theta, that might be profitable because you see what we have then? This piece I could call dv. This piece I could call u, right? So if u is equal to tangent theta, du is equal to secant squared theta d theta. And v, well, if dv is equal to secant theta tangent theta d theta, then let's see here. That makes v equal to what? What's the integral of secant tangent? Just secant, yeah, secant theta. The derivative of secant is secant tangent, so this is just secant theta. Derivative of tangent theta was secant squared, so, but this is the other sort of basic integral lurking about in the world of secant and tangent. So what we have then is the natural log of the absolute value of secant theta plus tangent theta. I'm starting to want to call that Pac-Man or something, but I haven't yet. Let's see here, plus uv, which is what? Plus tangent theta times secant theta, right? Then what? Minus the integral of what? Minus the integral of v du. Now v du here would be what? Secant theta times, yeah, secant cubed theta. Secant squared theta d theta. Oh, hey, and now we're done. You see, because as you guys were just pointing out, that's secant cubed theta. That's what we're after, right? So here's minus the integral that we started. Here's the integral that we started. So you do algebra, and you get 2 times the integral is equal to the natural log of the absolute value of the secant theta plus tangent theta plus tangent theta secant theta. And so the integral of secant cubed theta d theta is in fact 1/2 the natural log of the absolute value of secant theta plus tangent theta plus secant tangent. Plus a constant, of course, for good measure. There we go. Now, you're like, well, that wasn't too bad, right? I mean, I spent how many minutes on this? What, 5? But you got to think about how I got to the answer, right? Like, first of all, 8, apparently. I had the foresight to change the secant cubed to secant squared secant. I changed the secant squared to tangent squared theta, which is kind of a reasonable step given how the other ones work, right? But then the thought that I should do integration by parts like that, you know, the first time I did this calculation, it took me a while to come to that conclusion, all right? I'm just telling you, I think this is a harder problem. But there it is, there's the integral secant cubed. And I think once you see this, you probably have a shot at like integral of cosecant cubed, right? And you start to believe that we probably can integrate any power of the, you know, like secant or tangent. It's just a matter of unpleasantness. In fact, that's true. Because the secant or tangent powers of this, they ultimately reduce to some rational function in terms of sine and cosine, and those can be integrated. All right, enough about this. Let me move on then to perhaps a deeper magic. I don't know. Let's see here. So back to the imaginary exponentials, because we have more to do with them. I'll start by showing you something cool about them. So e to the I theta is cosine theta plus I sine theta, and e to the I beta is what? Cosine beta plus I sine beta, right? So these are things we should just, I mean, at this point in your life, you can just memorize these and accept them as fact. I can show you how, well, I can show you why they're reasonable definitions in complex, or you can derive them from other things, but that's not for here. For here, they're a super useful way of memorizing or remembering trig identities. Check this out. So if I have e to the I theta times e to the I beta, right? You guys know what has to happen here if this is a notation worth telling you about is what? This must be what? Yeah. Theta plus beta, right? But I factored out the I. Now, okay, so this is cosine theta plus I sine theta, right? That is cosine beta plus I sine beta. And then on the right-hand side, we've got what? Cosine theta plus beta plus I times the sine of theta plus beta. What happens when you multiply out the left-hand side, taking care to notice that I squared is minus 1? We get cosine theta cosine beta. I squared gives me minus sine theta sine beta, right? Plus I times, let's see here, cosine sine theta sine beta plus sine theta cosine beta. Now that's all equal to what's up here, right? So one of the really nice things about imaginary or complex numbers is every complex equation has two real equations in it. It's really kind of a slick notation. Because if I have a complex quantity is equal to another complex quantity, I get the real parts have to match, and I get the imaginary parts have to match, right? So what do we get from the real parts of this equation matching? Right, that's the adding angles formula for cosine. But you see what the difference is between memorizing it and deriving it here? I mean, you're like, well, I already have that memorized, so I don't need to know this. Well, if that's how you're going to think, I really can't. I mean, you go your way. I can't help you. But if you're interested in new ways of remembering things, this is very nice. So this is that, right? And not just remembering things, but understanding the interrelation between things. If you get yourself painted into a corner, this might help you derive your way out. So you notice, I mean, what I'm trying to say here is that we have now seen that these adding angles formulas for sine and cosine are a natural consequence of just the law of exponents for imaginary exponentials. This, I think, is pretty easy to remember. This is hard to forget, right? These, I don't know. When I was where you are, it took me some effort to try to remember those. When I saw this for the first time, I was like, oh, well, that's so much easier to remember. But anyway, that's me. Now, so there's another showcase of the use of this, but there's more. So suppose we want to find an identity for, say, well, let me just tell you the example which is prompting this discussion. Suppose you want to do something like integrate sine theta times the cosine of, I don't know, 7 theta, d theta. You can try to do that with U substitution. You can try to do that with integration by parts. But unless you've got a table of trigonometric identities, you're probably stuck on this one, right? With the imaginary exponential, I don't need a table because I can derive whatever I need, right? Let's see here. So let me just derive something more general. So what happens if we take sine of, let's say, theta times the cosine of beta? What does that give us? 1 over 2i e to the I theta minus e to the minus I theta times 1/2 e to the I beta plus e to the minus I beta. Now what I'm using here, of course, is if we solve these for sine and cosine, right, by addition and subtraction, what we derive is that cosine of theta is 1/2 e to the I theta plus e to the minus I theta. And we also get that sine of theta is 1 over 2i e to the I theta minus e to the minus I theta. So these, basically these things right here at the top in this method are what you have to kind of memorize. Otherwise, you kind of need these in order to make use of the method, all right? Again, you could ask the question, why are these things true? And that's a good question to ask in another course. Or maybe later in this course. We'll see. Now, so there, you see what I did? I just converted sine and cosine to imaginary exponentials because I can do algebra in imaginary exponentials. It's not a big deal. This is what, 1 over 4i, right? And what happens when you multiply these out? You get e to the I what? We get theta plus beta, right? Plus e to the I theta minus beta minus e to the minus I theta minus beta minus e to the minus I theta plus beta. Now I've written the exponents in a rather self-serving fashion. So, I mean, do you agree? Let's see here. Let me try to illustrate where those are coming from. Let's see here. So, like, obviously this times this gives me that, right? And you should see pretty clearly that if I look at this one times this one, theta minus beta, right? I get this one. Let's see here. I'm going to run out of markers here pretty soon. How about the product? Let's see here. This one times this one is giving me that, right? Because I've got a minus theta and a plus beta, but minus minus is plus, right? And then, of course, the last one is the product of the minus I theta and the minus I beta. So that's this one. What do we get? So you can regroup things here, right? We've got 1/2 of 1 over 2i e to the I theta plus beta minus e to the minus I times theta plus beta, right? And then, let's see here, plus 1/2, 1 over 2i e to the I theta minus beta minus e to the minus I theta minus beta. So let's see here, I just basically took this one and that one and grouped them together, right? But anyway, let me get to the point here. What is this? This is what? 1/2 sine of what? Mm-hmm. And there we go. That's a really nice identity that we can use in the future. So if we want a product of sine theta times cosine beta, it is in fact just that. So we can apply this to the example at the top, right? The integral of sine theta times the cosine of 7 theta d theta. And we have what? We have theta equals to theta, and we've got beta equals to what? Yeah. So this is equal to the integral of 1/2 sine of what? 8 theta plus 1/2 what? Sine of minus 6 theta, right? Seven plus 1 is 8, and 1 minus 7 is minus 6, right? You pull the minus out, what do you got? 1/16, minus 1/16 cosine of 8 theta plus 1/12 cosine of 6 theta plus a constant. And there you go. Again, this integral will remain mysterious to you unless you know some trigonometry. So you're like, well, these imaginary exponentials you're using, I don't care for them. It seems all hocus pocus nonsense. Well, fine, if you really feel that way. I mean, I guess I can't take you away from the real world. But I really wish you'd swallow the pill and join me. I mean, I don't know. You can derive these things with suitable massage of these formulas. I'm not going to try, but you could. Any questions? No?
Where did the sine of 8 theta come from?
Because theta plus beta is theta plus 7 theta.
Oh, okay.
Yeah. Are we good? Let's see here. What other things might we want to know? You might also face what? Something like sine theta, sine beta. And you would also possibly face what? Cosine theta, cosine beta. Let's see here. I'm going to be a little bit lazier. I think I can get something from this one, right? If I look at d beta of sine theta cosine beta, what do I get? That's the same as the derivative with respect to beta of what? 1/2 sine theta plus beta plus 1/2 what? Sine theta minus beta by what we just worked out. But you can differentiate, right? What do you get? On the left-hand side, we get minus sine theta what? Sine beta. On the right-hand side, what do we get? Differentiate with respect to beta, we just get what by the chain rule? 1/2 cosine theta plus beta, right? And then over here, by the chain rule, I get a minus theta minus beta, right? And so we can clean this up, and what do we get? We get that the sine of theta times the sine of beta is in fact 1/2 cosine of theta minus beta minus 1/2 of cosine of theta plus beta. So there you go. There's the identity for product of sines. So how do you guys think we can get the other identity, which we're still missing? You got options, right? You could go back to the imaginary exponentials, multiply it out in group terms like we did in the start, or we could do what? Say what? Take the derivative with respect to what? I think we could differentiate with respect to what? How about theta, right? Derivative with respect to theta of sine theta cosine beta, right? Now I hope there's a typo in the notes somewhere about one of these identities, and I hope I got rid of it, but I just, you know how you remember things and you can't remember if they were in a dream or from reality? I had that problem with whether or not I corrected this error, and so just you know, if you think there's an error, email me. Don't waste hours over it or something, you know. Every so often I get an email from a student like, I've been thinking for 3 hours about this line and I can't come to terms with it. And I was like, that's because it's wrong. You should have emailed me 2 hours ago, 2.5 hours ago. Okay, anyway, so there's the other one. Again, just an application. What if you wanted to integrate, say, cosine of 2 theta times the cosine of 3 theta? What would you get? So we get theta plus beta, which is 1/2 cosine 5 theta, right? And then what's the other one? So I mean, this is the theta. This is the beta. Sorry, I'm using some operator overloading here. Theta minus beta, so it's right? But of course, theta is even, so that gets eaten by the cosine. Theta is even, listen to me, cosine is even. So we got 1/10 sine of 5 theta plus 1/2 sine theta plus a constant. All right, once you have these three identities that we've just worked out, you can do any of these. Not a big deal, okay? But I think you can agree with me that this is actually a much more difficult problem, yeah? I mean, I don't know. Once you know this thing and that thing, then we can derive things, right? So these three formulas, they're helpful. Sorry, I meant you have a green dot burned on your retina today. I've been told I shouldn't call them an ex-student. It sounds like they're dead or something. A former student of mine went to China and she's like, "Could I get you anything?" I'm like, "I'd like a laser." So there it is. Don't worry, I don't try to get aircraft or anything. But I really think those pilots should toughen up a little bit. It's Chen shining a green light at them. We got to send them to jail. Come on. Now I can decorate my house. Ooh. It has other things. Maybe I'll bring them some other day. Sorry. I digress. All right, so we can integrate. You give me a trigonometric function, we can play these games and probably integrate it. All right, I think I've showed you a pretty good cross-section of the methods. So now I'm going to move on to something you probably will find more challenging. But you have less, I think there's less new trigonometry to learn in this. There's just really a couple of central tricks to what we're about to start. So I don't know. Who cares? Easy. Oh, no, no, no. I wanted to leave this for the next one. Dang. You know what happens if you put too much on here? It starts to make the letters will start sliding down the board. Ever seen that? Yeah, it's pretty cool. So I gotta, all right. Okay, so this brings us to the next topic, which is trigonometric substitution. And trigonometric substitution is related to U substitution. The difference between trigonometric substitution and U substitution, it's kind of the difference between differentiating a function and differentiating an equation, right? When we do differentiation of equations, we have to use this implicit idea, like y is a function of x. And so the substitution's kind of turned on its head with trigonometric substitution. But I could talk more about these general terms, but I think it's better for you to see some examples. So I'm just going to start with a pretty standard example. So just before I even do that, though, the principal goal of trigonometric substitution is to remove radicals. All right. Remove square roots. But it's a little bit more than that, actually. That's kind of, that almost belittles trig substitution, I think. I don't know. But that's what people usually say. Here's an example. Suppose we want to integrate the square root of 1 minus x squared dx. Right? Now, you can try the standard bag of tricks we have up to now. You'll fail. I don't think U substitution or integration by parts will do much for you here. I could be wrong. But what will work here is if we let x equals to, let's say, sine theta. Sidebar. U substitution, how did it work? Integral of e to the x squared times 2x dx. What do? We let u equals to x squared, right? So it's like integral of e to the u du, right? So this was the new, this was the old, See the difference here? Old, new. So the theta is playing the role of u. But I don't write an equation like theta equals something. I implicitly wrap up theta in some other equation which suits my purpose. This is an implicit substitution. Now, why do we do this? Well, what's 1 minus x squared if I make this substitution? Yeah, 1 minus sine squared theta, which is cosine squared theta. Yes. Which is pretty nice. What's dx? It's cosine theta, d theta. So you make these substitutions. Over here, what do you get? Square root of cosine squared theta. And then dx was what? Cosine theta d theta. Right? But the square root of cosine squared is just cosine. So I got cosine times cosine. I got cosine squared theta d theta. Like so. Notice that I know that I should choose the plus and the possible plus minus of the algebra because I started with what? My integral is what? It's the integral of the square root. So certainly its antiderivative should also be positive. Right? I mean, it's not even the antiderivative. This is a positive, a non-negative function. So after I make the substitution, it should still be the case. All right. Now then what? This is what? Integral of 1/2, 1 plus cosine 2 theta. Remember that? Like, it was so long ago we talked about that. When was it? Oh, yes, yesterday. But it's like, you mean to tell me that you're going to cover something one day and then expect me to know it the next? Yes. Yes, I will. That is how we roll in here. It's important to try to do your homework every day, really. At least a little bit of it. Otherwise, you'll start to lose track as we go on. And then, anyway, it all falls down. Are you with me? So we remove the radical, see, by converting the thing under the square root to a square. And then what? And then we use integral of trig functions, which we learned yesterday, and are still learning because you got to do your homework. And now we can integrate, which is what? We got ourselves a theta over 2 plus 1/4 sine 2 theta plus a constant. I can't do much better than this. Sine 2 theta, what could you... I'll tell you what, I'll write this. This is 1/2 times the inverse sine of x, right? I need to write my answer in terms of x, right? Plus 1/4 the sine of 2 times the inverse sine of x plus a constant. So here's the answer. Now, can we... man, I'm so happy about the way this stuff worked out. I really don't want to erase it. I guess they probably need to see me multiply it out, don't they? Fine. So can you guys think of anything we could try to... I think this is what I call a naked theta. Just a theta sitting out on its lonesome, just sitting there. Well, there's a half, but that doesn't help. There's really nothing I can do to make this prettier. This guy, on the other hand, the sine of 2 theta, there are things I can do to that. Like, what is the sine of 2 theta? What's that equal to? Can you break that down in terms of sines and cosines? I think we can. What was it? Well, I guess that's sine of theta. That's sine of theta plus sine of theta, right? What's wrong with me? I can't remember the identity. Isn't that 1/2 sine theta 2 cosine? It's 1/2. Oh, okay, so I got my half in the wrong. Yeah. Thank you. Duh. Now, this, I can write, like, there's a triangle associated to this substitution, all right? So this substitution here, but what's the triangle that goes with the substitution? Looking for a place to write. Say this is theta. X is equal to sine theta. So sine theta is what? Opposite over hypotenuse. So I think we can make the hypotenuse 1 and make the opposite side x, right? By the way, that's part of the reason we signed that homework problem earlier. So this would make more sense. Now, this is the square root of what? 1 minus x, right? So what is sine? So this is really what? 2 times x. What's cosine theta? Aha, see, so we can improve this answer. So what we want to do for the best answer is to write it as much as is possible in terms of algebraic functions. Now there's nothing I can do to that inverse sine really. I guess, well, we got a formula for natural log, don't we? We can rewrite inverse sine in terms of natural logs of something, is that right? Oh no, that was for the inverse hyperbolics, wasn't it? Yeah. I guess this is about as good as I can do. So anyway, I got 1/2 x times the square root of 1 minus x squared plus a constant, and there you have it. Let me just pause to do an application here. What if you want to find the area of this right here? So we should do what? We should integrate from -1 to 1 the square root of 1 minus x squared dx, right? If I solve for y, it's a, you know, the upper half of the circle, we have what? We've got y is equal to the square root 1 minus x squared if we solve for y. Now this then is what? This is equal to, apparently, 1/2 inverse sine of x plus 1/2 x times the square root of 1 minus x squared, big old parentheses. Can we use symmetry here if you guys don't mind? What can I do instead of, I can change the bounds from -1 to 1. Instead, I do what? What's the easier calculation? What's that? 0 to 1. What do I have to do if I do that? Very good. So by symmetry, we can do that. That cancels, at least cancels the halves. And we're just left with what? Inverse sine of 1. And you notice that this is 0 at both bounds. X equals to 0 makes it 0 at the lower bound. X equals to 1 makes the square root 0 on the upper bound. So anyway, we can neglect this. So we have sine inverse of 1 minus sine inverse of 0. Inverse sine of 1 is just straight up pi over 2. Inverse sine of 0 is 0. And there you have it. The area of the unit circle, half of the unit circle, is pi over 2. So trig substitution allows us to derive areas of circles, for example. This is something you couldn't do in Calculus 1, right? Well, how did you do this in Calculus 1? It's a typical mean test question. Find the area under this curve, right? And what you're supposed to do usually when that question is asked is just pull from the thin air that the area of a circle is pi r squared, apply that given geometric data to do the integral. Here I'm actually showing you the mechanics of how to do such an integral. Yeah. Are we good? I think you need to see more examples. what if we were to try to integrate, say, the square root of 9 minus x squared dx? So this time, what we're going to do is we're going to let x equals to 3. Looks like sine theta worked pretty good for us last time. If I let x equals 3 sine theta, then 9 minus x squared is what? It's 9 minus 9 sine squared theta, which is actually what? 9 cosine squared theta. And what's dx? It's 3 cosine theta d theta. So we make that substitution. We have the integral of the square root of 9 cosine squared theta. And then the dx, of course, gives me 3 cosine theta d theta. So I get the integral of 9 cosine squared theta d theta, which is 9 halves the integral of 1 plus cosine of 2 theta d theta, which gives me 9 halves of theta plus 1 half sine of 2 theta. Plus a constant, of course. Let me draw my little triangle, see if I can come to terms with a better way to make the formula. Here's theta. This time we've got x is equals to 3 sine theta, right? So sine theta is what? X over 3, right? So my triangle is a little bit different. Now I want to put 3 on the hypotenuse and x on the opposite side still. And what's the remaining side? This should usually happen in a trig substitution. As you draw these little triangles, the one side that's not immediately given to you by the substitution will be the thing you're trying to eliminate. We're trying to eliminate the square root of 9 minus x squared. In fact, that's what the adjacent side has to be. That's not an accident. This pattern happens over and over again. So what is sine 2 theta? Well, I guess 1 half sine 2 theta is actually equal to what? Sine theta cosine theta, right? But in view of the triangle, that's actually x over 3 times the square root of 9 minus x squared divided by 3. And so therefore, I find the answer, the integral of the square root of 9 minus x squared dx is equal to 9 halves inverse sine. So by the way, this says theta is equal to what? Inverse sine of what? X over 3 this time, right? X over 3. And then I guess I factored out the 9 halves. So 9 halves, big parentheses, inverse sine of x over 3. And we just showed that 1 half of sine 2 theta is in fact plus 1/9 x times the square root of 9 minus x squared plus a constant. Now, so let's see here. I'll show you one more example. Now, I'm going to give you the big picture tomorrow. All right, I'm just starting with examples. Tomorrow, I'll probably start with sort of an overarching comment. This is what you do in different patterns, right? So right now, I'm just trying to lay the lay the groundwork for understanding what's going on. So just some token examples. How about this? The integral of 1 over x squared plus 9 quantity squared. Now, so we had this identity earlier today, which was what? It was tangent squared theta plus 1 equals to secant squared theta, right? You know it. You love it. So if we multiply this by 9, it gives us an idea. So like 9 tangent squared theta plus 9 is equal to 9 secant squared theta. So if I look at this x squared plus 9, and I tilt my head and I squint and I think for a little bit, all of a sudden I get this idea, this thought, x should be equal to 3 tangent theta. If I said x equals to 3 tangent theta, then what do I have? I've got x squared plus 9 is equal to 9 secant squared theta. And what else do I have? I have dx is what? 3 secant squared theta d theta. So I can use this trigonometric substitution to change this to the following. So my dx is what? Dx is 3 secant squared theta d theta. And instead of having a sum of x squared plus 9 squared, right, which is insidious, I have what? I have 9 secant squared theta squared. Well, that's harmless. Right? That's just this squared, because this is that. How does that simplify? So you've got yourself what? A 3 over 81, 1 over what? Secant squared theta d theta, which is otherwise known as 1 over 27, the integral of, yet again, cosine squared theta d theta. It seems like this was not on purpose, by the way, guys. This is a total accident. All of my examples have come down to cosine squared theta after the substitution has been made. Completely accidental. Sorry about that, to be so boring. And then this is what? 1 over 54 theta plus 1/2 sine of 2 theta, just like we did other 2 times. It's a constant. Now, let me put the finishing blow on it. 1 over 54, tangent theta is what? X over 3. So I draw my little triangle. I've got theta, opposite side is x, adjacent side is 3. Hypotenuse is the square root of x squared plus 9. And so I've got myself inverse tangent of x over 3. And then what do we say? 1/2 sine 2 theta is sine theta cosine theta. So sine theta cosine theta is what here? X over the square root of x squared plus 9, right? Cosine theta is 3 over x squared plus 9 square root, right? And then, of course, you could simplify this a little bit more, but we got to go. So these are 2 of the 3 popular trig substitutions. Substitution to remove 1 minus something squared, sine or cosine or work. If you want to make something like a sum of squares simplify, we use a tangent substitution. If it's the other way around, if it's like x squared minus 1, we'll end up using a secant substitution. To every one of these, there's a corresponding dual hyperbolic substitution, which is sometimes easier to work out. So that's what we'll hopefully do tomorrow. Thanks, guys.